Welcome to the second lecture of the course Collaborative Robots Theory and Practice. So, in this lecture I will discuss inverse kinematic analysis of 6-DoF wrist partitioned arm. While doing so, I will be discussing what is kinematic decoupling. Let us start with a robot which is Fanuc CR35IA cobot arm. So, you see this is the robot, you see it looks like this. So, when you see the first axis, it is exactly vertical perpendicular to the ground if it is mounted on the ground. Okay. This is the second axis. What I could notice here, the first axis is perpendicular to the ground and the second axis is little off the, they do not intersect. The second axis and the first axis, they do not intersect. Rather, there is a gap in between that forms the link length over here, and this is your third link. Okay, move by the third joint, fourth, this is fifth. Let me bring it to the front. This is how it is, and then finally the sixth joint is like this. So this is how it look like. So what is peculiar to this kind of robot? So there are majority of industrial robot which are of this configuration only. So this forms the first axis and the second axis. There is a gap, and what else is to be noticed is this link. Okay, this link is not a straight link, rather it is an elbow shaped kind of. Okay, so it rises up and then it goes straight. So fourth axis forms the part of the link. So this is how it is. So now you see it has this gap which is clearly shown here. Okay, so there is a gap here that is given by 150 mm. Okay, that is this vertical axis and this axis. Okay, this is the gap. So there is a gap here, and then the link over here is something like this. This is your axis. Okay, so the shape of this link is something like this. Okay, and vertical axis and the first axis after that is like this, there is a gap. So this is the common architecture of industrial robots. So that is how this Fanuc cobot arm is also of the same configuration. It looks exactly like an industrial robot arm. Okay, so we will do inverse kinematics of this. Before to this, let us convert this model to a 3R stick model. 3R means up till this joint. Okay, before the spherical wrist, I will go till here. So the first axis, the second axis, the third axis, and finally it reaches till here. That is the center of the wrist center point. It is 3R stick model of Fanuc arm. Okay, up till the wrist. Okay, the DH parameter based on the dimensions which are here 1180, 790, 150, and finally the length up till here, that is from here to here it will come. So that makes it like this. So it is 150, 790 and 860. So this is a regular 3R special arm. In earlier case you saw the first link was like this, second was like this, and the third one was like this. Okay, but in this case the first link is like this, which is shaped like this, the second one comes like this, and the third one that goes like this. Okay, the first joint, the second joint, and the third joint are like this. So there is a gap in between the first axis and the second axis. It was not the case in case of standard 3R special arm. Okay, so I have to consider this distance also now, because this is a subset of first three axes of Fanuc CR35A arm. Okay, so this is how I have split it into a 3R stick model. Okay, now I have to do inverse kinematics of this. Not just this link is, now you can see this link, if I put it in this orientation, you see this link is something like this. Okay, so now I have to consider this 150 length also. So that has to come here. Okay, now the modified stick diagram would be 150, that accounts for this distance, 790, that is this distance, 150 again, that is for this distance, and 860, so that is this distance. So overall my 3R stick model for this robot is like this. Okay, this is very much near to standard 3R special arm. So this point can go to any position in x, y, z location, and you have to solve for the axis angles. First axis theta 1, the second axis theta 2, and the third axis, that is theta 3, and this will be given, that is x, y, z. Okay, so this is the problem which I need to do inverse kinematics for. Okay, so now let us convert this link, the third link, which is a bent link, okay, to a equivalent 3R special arm kind of, so that it becomes easier addressing the inverse kinematics problem of this. So instead of taking it like this, that is a elbow kind of structure, I will consider a equivalent link that starts from here and goes till here. This is a link replacement. So instead of using this, I will use this one. Okay. So what is my equivalent link length then? It will be 150 square plus 860 square and root of that. Okay, so that comes out to be 872.983 mm. So this is my new link that I have put. Okay, now when the link 3 makes an angle 0 degree, okay, this theta 3 is 0 degree, okay, in that case this at home position would be 9.894. This can be easily calculated using tan inverse of 150 by 860. So that angle is 9.894 degrees, which it has in its home position also. So this is the start angle of this link, and you have link length of 872.983 mm. So this is how the new DH parameter would look like. So new link length would be 872.983 with starting angle as this. So now the Fanuc theta 3 would be initial angle theta 3 alpha, whatever is the angle which this covers, okay, this is the additional angle which is always present there. Okay, so that angle needs to be accounted for. Now I can do standard inverse kinematics of this arm in a way very much similar to this. So instead of 860, it is now 872. So this is my home position angle. When Fanuc shows it as 0 degree, that angle would actually be tilted something like this. Okay, but the real Fanuc will show me this angle. Okay, so when it is horizontal to ground, it already makes some angle from the ground. So that I call it as theta 3 alpha. Okay, that is theta 3 alpha. Okay, so that is the additional angle that accounts for the joint angle theta 3 plus this permanent angle, that is alpha, that is 9.894 degree. Now I will start solving for this. For any given position x, y, z, this robot will configure like this. So here comes your theta 1, this is your theta 2, okay, and you have theta 3. Actually theta 3 would include the, so this is your new link length, that is the equivalent link that you have put, and that makes a permanent angle apart from theta 3. It will have an angle alpha also, that makes it theta 3 alpha over here. Okay, so that is how I have put it so as to make it very simple. So forward kinematics will lead to this, okay, that is A1 plus A2 cosine of theta 2 plus A3 cosine of theta 2 plus theta 3 alpha. Okay, so whole of that will come like this. So that is your Ex dash, that is equivalent coordinate And again this is very much similar to a planar arm kind of. So this is a plane. So this arm always remains in a plane, and the plane rotates by an angle theta 1 from initial x axis, that is the original x axis. Got it? So total z in that case would be d1, that is the height if at all it is here. So this is your d1, that is the stand height for the Fanuc arm. So d1 plus sin A of this plus sin A of this. So those two things will come here. So this is your forward kinematics. Using this, I look for my 2R subset again. That makes things quite simple. Okay. So for Fanuc, this d1 is equal to 0. I have put the origin over here. Alpha is this. Using the first two equations, this and this, what I got is, by dividing this by this, I got tan theta 1 is equal to y by x. So theta 1 is equal to 8 and 2 y comma x. So I got immediately theta 1. What needs to be obtained now is theta 2 and theta 3 alpha. If I again put down like this, so E x dash, so that is can be derived by dividing x by cosine theta 1 is already obtained. So this is it. So this comes here. So that is your E x dash. So that is from here to here. Okay. And again E z dash is from here to here. Okay. So E x dash and E z dash. So that is now, if you can remember, it is exactly similar to a 2R arm. If it starts from here, so this 2R arm remains in this plane. Okay. So now this is equivalent to 2R arm with the links 2 and 3. These two are its links in the plane x dash z dash, which is rotated about actual z by an angle theta 1. Okay. Using this, if I know E x dash and E z dash, I can quickly obtain angle theta 2 and theta 3 alpha using our 2R solution. Okay. That is put here in the same way, and theta 2 and theta 3 can quickly be obtained. Okay. So that is your solution, but this theta 3 is not exactly theta 3. Theta 3 alpha can be used to get the theta 3 like this. So theta 3 is actually theta 3 alpha minus the alpha angle. Okay. So this 3 alpha included theta 3 and the alpha angle. So that alpha needs to be deducted to get the actual theta 3, which is shown by the robot controller. Okay. So that is what can be obtained. Okay. So number of solutions here again would be 4. This link is like this. Got it? This is how it should look like. Okay. And this is your first link, and you have elbow up and elbow down solution. Again it will come something elbow up and elbow down. The one which is here is elbow down solution. You can have an elbow up solution also. And the first angle theta 1, that is A tan 2 y comma x, gives you theta 1 and pi plus theta 1. So it should be all in the front or it at the back and come back and touch to the same point x, y and z. So this is how it is. So the first angle would be 100% behind. So if this is theta 1, the next one would be theta 1 plus pi. The arm will go back and it will, from back it will again come back to the same point. Okay. It is not always possible for a robot to take up this mathematical solution. It may not be physically possible. So if I use the same solution which I have obtained here, okay, for theta 1, 2 and 3, I can use my standard coding. I have used MATLAB here to do this. It will look like this. So you can see the stick diagram of the complete robot here that includes all the distances. So this is your D1, okay. From here to here it is your A1, this is A2, and I formed the equivalent link that looks like this. This is your alpha, and you may have some angle also. In this case it is theta 3 is equal to 0, okay. So that angle comes here. So this rotates like this rotates like this, and this rotates like this. This is theta 3, theta 2 and theta 1, okay. So this is how. So if I put for a sample value the state of the robot as shown in this figure, this is the coordinate which I should be putting for Fanuc robot, okay, and this gives me theta 1 is equal to 0, 2 is equal to 90 degree, theta 3 is equal to 0 degree, okay. So you have to take care of solutions where you can see at the denominator 0, that you can exclude, okay. You can have 8 and 2 implementation here as I have done it over here, okay. This is how inverse kinematics right up till the rest is solved, okay. That is using the first 3 links of the robot, which helps you to position a robot to a particular pose, okay. And then you need further 3 degrees of freedom to orient it, okay. So now inverse kinematics using kinematic decoupling. So up till here it is 3 degree of freedom, 3R spatial arm, okay. This is Nachi robot CZ10 cobot, okay. Till here it is 3R, okay. The architecture of this robot is also similar to the one which is used by Fanuc, only the dimensions are different. So till here it is this, okay. After that it is another 3 degrees of freedom. So that goes like this. If you take up this from here, so this is your axis that comes like yaw, okay. And then you have pitch axis that is here, okay. And then you have one more axis that is like this. So that finally comes out like this, that is roll, this is pitch, this is yaw, okay. So you have all the 3 axes intersecting over here, and that is known as spherical wrist. It behaves like a spherical joint which can attain all the 3 rotary motions, okay. A given 6 degrees of freedom robot can be decoupled using inverse position kinematics and inverse orientation kinematics. Now there are 2 problems. If you know the wrist center point, that is this point, okay, you can do inverse position analysis the way you did it in the last example, and remaining 3, if you know the orientation, you can solve for remaining 3 are spatial robot needs to be solved. For orientation we will use this, for positioning we can use this. So this is known as wrist partitioning based approach to solve inverse kinematics, okay. So now let us continue. So this is another robot, Staubli TX2 Touch 90 robot. This also has got a similar configuration with wrist center point somewhere over here, okay. Now steps to do inverse kinematics for wrist partitioning based approach using trigonometric and vector approach only, okay. So what is my input? Input is the end effector position that is given by, if this is the 6 degrees of freedom robot, this is joint 1, joint 2, joint 3, 4, 5 and 6. Finally you reach till here. So this position is known, the position of end effector that lies here is known. So this position vector is known, which I have written it as O6 with respect to the base frame, that is O, okay, that is 0, okay. So end effector position is known, and orientation, if you know the roll pitch yaw angle of the end effector, okay, RPY is known, you can quickly convert it to the rotation matrix, that is, if you know the roll pitch yaw angle, so if you remember your Euler angle conversion, okay, roll pitch yaw angle, you can convert it to rotation matrix using this. So, rotation about x, y and z. If you know roll pitch yaw, so that can be used to convert it to rotation matrix of the end effector, and this is with respect to the 0 frame again. Okay. So, these two things are known, the 0R6 is known, 0O6 is known, position and orientation. So, what I need to find out is all the joint angle theta 1 to theta 6, because this is a 6 degrees of freedom robot. So, next step is using the known values, okay, solve for the first three joint variables theta 1, theta 2 and theta 3 such that the wrist center 0OC has the coordinate which is given by this. Okay. So, the last length is known. Okay. This offset can be extracted d6 from the technical specification. If you created it, created the ds parameter table, so this is coming under d6, that is joint offset, distance travelled along z axis. So, it was this 6, this is your z5, is it not? So, this is your 5, okay, 5, 6 and 4 all are intersecting at a point. Okay. So, use inverse kinematics solution for 3R special arm. Now, if I know the location of this point, wrist center point, okay, the remaining arm is a 3R special arm and I can quickly find out. So, 0OC is known using this. So, if this position is known, this is known using this d6 is known, but d6 is known, this vector is known in its own frame, that is about this frame. So, it can be written as d6 0 0 1 or 0 0 d6, because this is the distance along z. Okay. So, it is 0 0 d6. Okay. That is with respect to this wrist. Now, I have to convert this with respect to the base of the robot, so that I can do vector addition or subtraction. We can use this vector triangle now. This is known, okay. D6 is known, but it is in local frame W. I will convert it to frame O, so that D6 is now represented in O frame again, and I will use vector triangle to find it out, 0C, that is the wrist center point location. This is how it is done. So, if you multiply this with the rotation matrix 0R6, what do you get? This is now vector d6 in 0 frame, okay, that is O frame. This is how it is made to come in the same frame. Now, I can use vector triangle to find out 0OC. Okay. So, this is how I have obtained the wrist center point. As soon as I have obtained it, okay, so using this and the joint angles theta 1, 2 and 3. So, I did what? I did inverse kinematics and solved for theta 1, theta 2 and theta 3 now, that is using the earlier solution that I have showed you using 3R special arm. I got to wrist center point, I solved for theta 1, 2 and 3. Using the joint angles obtained in step 2, I will compute what? 0R3. Now that I know theta 1, I know theta 2, I know theta 3, I have the DH parameters already. This is D1, A2 and A3. Okay. So, I know the dimension, I can quickly compute 0R3, that is the part of transformation matrix 0 to 3. Okay. So, you have 0R3 coming here as 3 cross 3, and then you have position of wrist center point over here 1 0 0 0. So, this is where you can obtain 0R3. Okay. So, you just do forward kinematics right till wrist center point and you can quickly obtain this 0R3. Okay. Now, I will use it. Okay. So, now I have following things in hand. these two are from given problem. Okay. Joint angles theta 1 to 3 obtained earlier, 0R3 in the previous step. So, you already know 0R6 is product of 0R3 and 3R6, that is rotation transformation from here to here and from here to here, that is the. So, now I can use again, I will do inverse of this. Okay. So, I can bring it to this side and I can calculate 3R6, that is from 3 to 6 I can quickly obtain like this. I will take inverse, I will do this. Okay. So, this gives me a set of values as a 3 cross 3 matrix, that is from 3 to 6 frame. I got the values here directly. Okay. Now, what I will do? I will use this again in the next step. So, now you have in hand is 0O6 and 0R6 joint angles theta 1, theta 2 and theta 3. If you have already in hand theta 4, theta 5 and theta 6, those are in terms of variables. So, using Euler angle system again, Z, V and W. Z is along this, V, this is called as V and this is called as W. Okay, I have used all the three rotations now, theta 4, theta 5 and theta 6. If you use this, I can quickly get 3R6 as this matrix. Okay, you can directly get this matrix from the Euler angle that was covered earlier in one of the lecture. Okay, so I can use, this is in terms of variable, these are not values, the values are already here that I have obtained. Okay, this is 3R6, these are the values. Okay, now both should be equated. Now this 3 cross 3 rotation can be equated to the one which is obtained in the previous slide. Okay, so this is in terms of variables, this is in terms of values, both should be the same. So, if I equate them here, so these are the values, these are in terms of variables. Now, one to one we can equate. Okay, using that joint angles theta 4 can be obtained. Okay, from Q23 and Q13. See where it is, Q23 and Q13. Okay, using these two, you see, you can quickly divide and you can find out theta 4. Okay, this by this is theta 4. Similarly, you can obtain theta 5 using Q13, Q23 and 33. Okay, Q13 is here, Q23 is here already. Okay, and Q33. So, last column can be used to find out this. From here you have obtained what? First two you have obtained theta 4, using whole of this you can use and find out theta 5. Similarly, theta 6 can be obtained from these two. You just divide and you can get it. So, all these are expressed in terms of arc tangent solution, 8 and 2 solution. Okay. So, theta 4 and 5 and 6 can be obtained. This is the alternate solution which is 180 degree apart. With this you can quickly obtain the all the angles, that is theta 1, 2, 3 using 3R special solution, and using the RIS solution I could find out theta 4, 5 and 6. Okay. So, this is how any robot of this kind can be split into a positioning problem and a orientation problem, and it can be solved like this. Okay. That is all for this lecture. In the next lecture, we will do inverse kinematics of UR arm, that is a broad set of robots which look like the same. So, all the robots will belong to the same category and will solve for it. Okay. Thanks a lot.